Are you kidding me?
Good morning, everyone. We're going to start by going very quickly over the worksheet I gave you, and I will ask different students to see what they think the substitution should be, or the integration technique should be. Do you guys have any questions before I start? Okay. So this is on Brightspace. I already put this sheet on Brightspace for you. And the questions is here. For each of the integral below, indicate the technique most likely to find an antiderivative. And the question is not do not compute the integral. That's not the point. And your answer should be one of the following: either integration by parts, what's the u, what's the dv, partial fraction decomposition with the form of the decomposition, direct substitution with your choice of u, trigonometric substitution was the most suitable trig substitution. Okay. So this is the question. So we start with the first one. A, what is the best approach for this integral? And go ahead. Direct substitution. If it's direct substitution, what's your choice of u? So direct substitution. And the choice of u is u square, absolutely correct, Emilia. Now, part B, quickly. Part B. What type of substitution this is? Trigonometric substitution. And if you do trig substitution, what is the substitution?
Secant.
X equals secant, not half correct. Half correct.
Oh, 3 times secant.
Crucial, crucial. Actually, I was grading your quiz. A lot of you forgot the 3, and it's wrong, nothing worked. And why the 3 is important, since actually it was brought up anyway. The importance of 3 is the following. If a student missed the 3, then write 3. And the student who wrote secant squared theta minus 9, when say substituted in the expression square root of x squared minus 9, nothing happened. I mean, square root of secant squared minus 9 is nothing. You need secant square of theta minus 1 to get the tangent square. So if you have minus 9, this is not that. This is not this, nothing. So you have to have a 9 here to be able to factor it out. And the only way to have a 9 is for x to be 3 secant theta. And then when you square it, you get the 9. And now you can factor it out and get the tangent. Okay, so a lot of you on the quiz, you did not put, it was an A, you forgot to put an A, and the whole problem collapsed. It doesn't really work. All right, part C. Part C quickly. I feel too quiet. What's part C?
Would it be integration by parts?
It has to be integration by parts. Okay, whenever you have, and the integration by parts, what are the parts? What are the parts? It means what's the u and what's the dv?
U would be ln of x, and then the rest would be dv.
What's the rest?
1 over x times the square root.
Exactly. The rest is 1 over x, square root of the x dx. or because you need to integrate that, x times square root of x is x to the power 3/2. So the dv would be x to the minus 3/2 dx. Absolutely important. Okay.
I have a question.
Yes, please go ahead.
I get really confused about integration by parts. How's it different from just U substitution?
It's no very different. There is no substitution. You're not creating a new variable in here. You're not creating an integral with a new variable. So the integral is just you're using basically the product rule. So here, when you write integral of u dv is uv minus integral of v du. You're not substituting anything for x. You're just choosing a formula. So when you do that, the variable basically is still x. You're just substituting this with a simple integral. So if we do this particular problem, my u is ln of x. That's not the substitution u, and the dv is x to the minus 3/2 dx. And then it's going to be u v. Now, if you find the antiderivative of that, you get 1 over minus 3/2 minus 1. So you're going to get 1 over that. So you're going to get a 2. X to the minus 3/2 plus 1 minus a half. So you're going to get like a minus 2. Okay. So it's going to be ln of x times minus 2 x to the minus the half minus 2 times the integral of v. So it's the same variable. Du is the 1 over x dx. I'm not really changing variable. I am basically using a formula that substitute this integral in x into this new integral in x. And then I just finalize x to the minus a half over x, which is going to give me x to the minus 3/2, and then I just integrate. Okay. Now, when I'm doing substitution, like this one, I'm introducing a new variable. U become my new variable. Du is 2x dx. I'm transforming this integral in x into a new integral in a totally new variable. We're basically doing the chain rule in this case. So a very, very different approach to integration. Here I'm creating a new variable and expressing my old integral in terms of my new variable. Here I'm not introducing a new variable. My variable is always x. I'm just using a formula that transforms this integral in x into an easier integral in x. Make any sense?
Yes. Thank you.
Are you sure? Okay.
Yeah, I'm starting to remember now.
Yeah. Okay. D, quickly. Partial fraction decomposition. Okay, absolutely, because that's a rational function, a polynomial over a polynomial. And whenever you my question is, what's the form of the partial fraction decomposition? What's the form of it? So what do you do to get the form?
You gotta factor out the bottom first. Factor out
Factor
x.
out the bottom. Okay, so this is gonna give me x times x squared minus 1. That's not enough. I have to keep zooming in till I factor completely. And now every factor is linear. Every factor is linear. There is nothing to it. Every factor is linear. That's the contribution. Okay. All right. E, quickly.
Direct substitution.
Direct substitution. What's your U?
1 over t.
You are very good. The U is going to be 1 over t. The reason is when you find the du, the derivative of 1 over t is minus 1 over t squared dt. which is basically going to pick it up right there by this term right here. Okay, F.
Would that be direct substitution also?
Think about it. Will direct substitution help me a lot?
Well, not really because of the pi.
No,
Oh.
that's not my issue.
They're both the same degree.
Right, I have an x in here. So even if I put u, suppose I make the substitution, u equal, if I make the substitution, what do you want substitution? You want u equal pi x? I can do that, but it does not really get me very far, because then what's going to be the integral? The sine of pi x would become the sine of u, correct? The du is pi dx. So the dx is 1 over pi du. Fine. But what about the x here? The substitution will not get rid of x. So I will still have u over pi. Because if I substitute for x, it's u over pi. So in either problem, I'm transforming an integral in that into the same type integral. The substitution did not really get me anywhere. However, in the first problem, as your classmate tried to tell us, that in this first problem, if I put u equal x squared, the du is to x dx. So that's almost, the x dx is almost the derivative of x squared. That's where substitution works. We should have a function and its derivative as part of the integral. That's my inside, and that's the derivative of the inside. Here, substitution will work. Here, it gets me nowhere. I did the substitution, but I have the same type of integral. I ended up with u sine u. So what's the best way to do this problem quickly? Please hurry up.
Integration by parts.
By part. This is by part. Okay, there is no way out. That's by part. And what are the part?
U equals x and dv equals sine pi of x.
Dx. Okay. And then use by part formula, problem is no. Okay, the following one. E. Okay. Right. Anybody else? You agree with what's written on chat? So, direct substitution, because I have the 9x squared plus 4, and its derivative is right there, part of the integral. So this is direct substitution. No way else. Okay. H. You guys, I've told you to look at those. H.
Trigonometric substitution.
Trig substitution. And whenever you have trig substitution, what is the best substitution possible?
Two-thirds of a tangent.
The third tangent, okay, because, I mean, that's absolutely correct. And if you remember, I told you last time, the way I memorize it is that the first piece is 3x squared plus 4. So the way I see it, if we remember, to get a secant square, I need to set the 3x to be 2 secant theta. It means my x is 2/3 secant theta. That's the way to go. All right, I.
Would that be partial fraction decomposition?
Partial fraction decomposition, absolutely correct. And so this is partial fraction decomposition because I have 1 over 4x squared. There is no substitution inside because even if I put u to be 4x squared minus 1, the du is not there. So partial fraction decomposition, and all right, you know what to do. What you want me to do? Factor it out. How do you factor out the denominator quickly?
Two x plus 1, 2x minus 1.
2x minus 1, 2x plus 1. Problem is basically done. So that's going to be 2x minus 1, 2x plus 1. Okay. All right. J.
I have a question real quick.
Please go ahead.
For number I, wouldn't it be ax plus b and then plus
J.
cx plus d, or
J. Do the following one. How do we do J? Quickly.
Partial fraction.
Partial fraction. Again, that's a polynomial over a polynomial. There is nothing inside. All right, so partial fraction. How are we going to do it? Keep talking. The student who's talking to keep talking. Remember, I don't know who's talking, so
Factor out an x on the bottom.
we're gonna factor out the
Yeah.
x on the bottom.
And then that factors to x minus 4 times x plus 1.
So that's factor x minus 4. Are you sure?
Oh, no, it doesn't. Sorry.
Yeah, it doesn't. So can this be factored actually? Maybe, I didn't know. I didn't try it. What's the b squared minus 4ac? It's 9, right? Minus 4 times 4, 16. Negative. There is no way you can factor this term. Yeah, it cannot be factored. All right, so you cannot split it. Yeah, you tend to think 4 and 3 is 4 and 1. No, it doesn't work. And this is to the student who asked me the question about the x plus c. When I need to write the partial fraction decomposition here, how it's going to work? You have two factors, x and this term. This is quadratic. It means there is a square involved. A quadratic that we cannot factor it. Whenever we have a quadratic that we cannot factor it, then this expression is contribution to the partial fraction decomposition is the bx plus c. So whenever it's a quadratic that cannot be factored, that's its contribution to the partial fraction decomposition. So it has to be quadratic. Not only that, we cannot factor it. It means we cannot write it as the product of two linear terms. So if it's linear term like this, or repeating linear, and then there is no bx plus c, there is bx plus c only if it's a quadratic term that cannot be factored. The student who asked me the question, did I answer it?
yes? Thank you.
Suppose I have the following, another simple scenario. So suppose I have the following expression. Okay, I'm going to give it a totally. Suppose I have 1 over x minus 1, x plus 1 square, x squared plus 4. The general scenario. And I need to write the decomposition of that. And this is decomposed. This is factored. One factor, that's linear. It means that it's not quadratic x squared. That's linear, repeating. And this is quadratic that cannot be factored. So now the contribution of its term like this. The x minus 1 stay x minus 1. The contribution of this is a constant over x plus 1 plus a constant over x plus 1 squared. This term that I cannot factor, its contribution is dx plus e over x squared plus 4. That's the picture. And the idea is that we have to decompose it so that we can easily integrate each term. And in this scenario, that's easy to integrate, easy to integrate, easy to integrate. And this is, we've talked about it. You split the numerator and you can proceed. So the idea is to create a scenario where the decomposition is much easier, where the integration is much easier. So that's when we have the dx plus e. Quadratic cannot be factored.
So it has nothing to do with what's in the numerator.
No, and as long as the beginning, the degree of the numerator is less than the degree of the denominator. That's what we have to be careful with. If the degree of the numerator is greater or equal, then we have to do long division, and then we proceed this way. Okay? Yeah. Actually, I would like you to finish this for tomorrow, and we will discuss it. And today I'm going to start another idea, but you guys make sure you can finish this, and please start working on your review for the final. Okay, so please finish this, because you have to put the whole thing together. You have really to put the whole ideas together for this exam. Right. So today we're going to start section, oh, I forgot the number of the section. Sorry, improper integral. You can look up the section in the book. Improper integral. Okay. So before I start the section, I have to remind you a little bit very quickly. So a quick review of limit. So we're heading in the course to a part of the course where we need the idea of limit continuously. So quick review of limit. Because that's where we're heading. All right, so I will ask you very simple questions, because as I said, it's a very quick review. So very simple question. What's the limit? X goes to infinity of 1 over x. As I said, very simple, but I want answers very quickly. So remember what this means. Limit as x goes to infinity. It means when x starts taking very, very large value. That's how you have to understand limit. What happened to 1 over x?
Isn't it 0?
It's equal to 0. If you ever forget, it's not a big deal. I take large value, 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000, and start asking them, you know, what's happening to those when x becoming large? All right, another simple limit. And I say simple because my goal is to remind you of this. What's the x goes to 0 of 1 over x? And as you realize, I put 0 positive. It means larger than 0, but very close to 0. What's this limit quickly? So again, you start
Infinity.
thinking. What?
Infinity.
It's infinity. You start thinking. If you panic, okay, you take 1, you divide it by something very, very, very tiny. One way you can think about it, if you have something of length 1, you divide it by a lot of small pieces. You're going to get a lot of pieces. Okay. Or if you don't want to think about it this way, when x is 0.1, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, plug in value and realize the number is getting smaller and smaller. What's the limit when x goes to 0 from the negative of 1 over x? X still small, but x is negative. What's the limit?
Negative infinity.
Negative infinity. What's the limit as x goes to 0 of 1 over x?
Undefined.
Indefined, because from the positive is plus infinity, from the negative is minus, does not exist. How about the limit as x goes to 0 of 1 over x squared?
That's infinity.
That's plus infinity, because regardless how x approaches 0 plus negative x squared, is going to be a positive number, very small positive number. Okay. All right. Let's keep going along the same line. What's the limit of ex as x goes to infinity? Please.
Infinity.
Infinity. Okay, e to the x, graphically, it looks like this. That's e to the x. When x gets very large, e to the x, I mean, you just plug in value, e squared, e to the power 5, and so on and so forth. You're going to get a very, very large number. What happens e minus x when x goes to infinity?
0.
0, because absolutely correct. 0, give me a reason, a quick reason, easy reason.
Isn't it because like E makes the X like super big, so if it's negative, then it'd be wait. Okay, wait, I think I thought of it wrong.
You can make it 1 over e to the x. And
You
then
can make it 1 over e to the x. That's the easiest scenario. Okay, when x goes to infinity, e to the x is going to become very large. 1 over something very large is very, very, very small. Okay, so when you take x goes to infinity, it means you're raising e to a very, very large negative 1, which is 1 over e to the positive 1, which is equal to 0. Now, what's the limit as x goes to infinity of the ln of x? So those are the basic function we're going to work with. And to be able to work with those functions, crucial picture is this one. Okay. When x goes to infinity, what's the limit of ln? Is plus infinity. When x goes to 0 from the positive, so x gets very small, positively small, and the limit here is minus infinity. Okay. So those limits, they have to be basically totally memorized, totally known, because they are crucial for us. Now, another type of limit that, again, we've talked about it in 163. So indeterminate form. Okay. So here I will write a parenthesis. I remind you what they are, but first let us remind ourselves where they came from. And the idea is, suppose I tell you find the limit as x goes to infinity of, let us say, x squared over 2x squared plus 5. So what's the problem here? The problem is that when x goes to infinity, my numerator goes to infinity and my denominator goes to infinity. And the problem was, if you guys remember when we talked about 163, when we have a large over a large number, we can have anything. We can have a large number, we can have a small number, everything can happen. Okay. And this depends how fast the numerator goes to infinity and how fast the denominator goes to infinity. It's like taking number. If I take 10 to the 10 over 10 to the 5, they are both big, but the ratio is big because this is way, way, way bigger than that. However, if I flip them around, this is going to be 10 to the minus 5. So that's going to be a small number because the denominator is way, way bigger than the numerator. So that's type of form. When we have numerator and denominator goes to infinity, we have a specific name and we call this is indeterminate form because we don't know what the limit. We have to manipulate to get the limit. The same scenario occur if both numerator denominator goes to 0. The same scenario occur if you're multiplying two things and one go to 0, one go to infinity. Then the product can do anything they want. Let us remember, how do we compute this limit? You guys remember. quickly because I need to move on. And we've done this in two different ways.
Take the derivative of the top and the derivative of the bottom.
Yeah, what did we call this? You remember?
Chlorpetals rule.
Right. We can do that in two ways. So find in two ways. Okay, the first way, use Chlorpetals rule. Use Chlorpetals rule, and this tells me that the limit of x squared over 2x squared plus 5 is the limit of the derivative of the numerator over the derivative of the denominator. Which is going to be equal to the limit as x goes to infinity to x over 4x 2 over 4, which is a half. Okay, so this, but we can do it by using Chlorpetals rule, which tells me if you have indeterminate form of type infinity over infinity or 0 over 0, then the limit of f over g is the limit of f prime over g prime. Okay, and that's what's crucial to compute limit, and we're gonna start using it, I mean, in this, starting this section and all the way the whole next chapter. Another way to do it, or remember the other approach to this kind of limit, this specific type of limit.
Divide each by the highest degree.
Exactly. So we can divide numerator and denominator by x squared. That's another way to do it. And then we will get the limit of 1 over 2 plus 5 over x squared. Okay. And then this will go to 0 because 5 over something very large is 0. And this would give me a half. Okay. So that's some review of how we're going to deal with limit. I will take 2 more examples and then we proceed to the idea of improper integral. Right. So another example is limit. Suppose I have limit of x goes to infinity of x over ex. Right. Let's see what happened here. When x goes to infinity, this goes to infinity because it becomes very large, and ex goes to infinity. So I have infinity over infinity. And the question is, what happened to the ratio? When I take ex over ex, what happened to that? Okay. All right, we're going to do it Chlorpetals rule, and then we're going to a little bit talk about it because that's an important limit. And what happened here is important. So infinity over infinity, we can use Chlorpetals rule. It means it's the limit of the derivative of the numerator over the derivative of the denominator. Means the limit of 1 over ex. Now when x goes to infinity, this is a 1. This will go to infinity. And 1 over something very large is going to be equal to 0. Okay, so if I take x over ex, the limit is 0. It means intuitively, which one goes to infinity faster? It means when x is large, which function takes larger value, the x or ex?
Ex.
Ex. Actually, how much faster? Let us pick up very few value of ex, compare them to x. So this is x and this is ex. I'm going to take very few value. I'll pick up my calculator for that. Very value. And we see how fast each one of them goes. So what do I mean by very few value? So I'm going to pick, for example, x to be 5, 10, and I think the picture will be complete. If I take e to the 5, so this is my calculator. and I take e to the power 5, it's 148.41. So if x is 5, the e to the 5 is 148 point something. So already you can see that when you're going to take the ratio, it means you're going to take 5 over 148. You already know that how small this is going to be. So if you take x equals 10, e to the 10 is huge compared to x. It's absolutely huge. It's 22,026 with a bunch of numbers. So we're going to take the ratio. It's going to be very, very, very small. So this is comparing the ex to x. E to the x goes to infinity very fast. Not only very fast, it actually runs to infinity. It means it starts taking huge value for small values of x. So it goes to infinity way, way, way faster than ex, causing the ratio to become actually very small. Very important behavior of x over ex. And the idea is that even if I take, instead of x, suppose I take x squared over ex, do you think the limit is going to be 0 based on this table?
No,
Why?
I think because EX is still gonna raise it higher.
Right, so what's going to happen to the ratio? It's going to be small. Which can I take? What you said is correct. It means which take when x becoming large, which one is larger, x squared over ex or ex?
EX.
Yes. So in take the ratio, what's going to happen? It's going to get smaller. Because look at the picture. When I take x squared, so suppose I take x squared over ex, it means it's going to become 25 and it's going to be 100. That's really the only difference that's going to happen. Look how much bigger the ex is. Even if I take x squared, it doesn't really matter. So the ratio is going to be also equal to 0. And if I use L'Hopital's rule, I will get 2x over ex. That's L'Hopital. And I need to, still, I have large over large. I use L'Hopital's rules again. I will get 2 over ex, which is equal to 0. So ex goes faster to infinity than x. It goes faster than x squared. It goes also faster than x cubed. Because even if I put x cubed, nothing will change. That's going to be 1,000. It's going to be 22,000. It's still small numbers. And the idea, regardless what power of x I take, the ratio is going to always go to 0. So ex grow faster than x to any power you can think of. Another limit of importance, or another behavior that's important for us, is the ln of x. So suppose I compute the limit tend to infinity of x over ln. And the question is, which one will go to infinity faster? So it's going to be, this is equal to. First, I apply L'Hopital. When x goes to infinity, this goes to infinity, and this goes to infinity. Then I will have large over large. I will apply L'Hopital's rule, and I will get the limit as x goes to infinity of. The derivative of x is 1. Derivative of ln is 1 over x. For those who forgot L'Hopital's rule, absolutely crucial you remember it. Check it because I will need to use it a lot. So that's the limit as x goes to infinity. 1 over x, algebra tells me that's x, which is equal to infinity. So now let us analyze which function goes to infinity faster, x or ln. So I'm going to make a table just like I did before to compare the values. So you see what's happening. This is x, this is ln, and then we look at the ratio. So I'm going to take, let's 5, 10, 100, 1,000. And I want to watch the growth of each one of them. Okay. Suppose x is 10. What is the ln of 5? 1.60. Okay. Then what's ln of 10? 2.3. Let's see what's ln of 100. 4.6. We should know that, but I want you to watch what's happening. Which one goes to infinity faster? ln of 1,000. 6.9. Okay. How does ln goes to infinity? Means when x is large, what type of values the ln take? They get larger, but very, very slow. They get larger, but very, very slow. Even when I took x to be 1,000, the ln is still taking the value 6.9. So when I'm looking at the ratio, what's going to happen? It's going to be large or small? This is 5 over 1.6, 10 over 2.3, 100 over 4.6, 1,000 over 6.9. And I can keep going. I mean, I can take larger and larger value. But which function takes over? The numerator x or ln? Obviously, x. Obviously, x is taking, when x is large, x is way, 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 way larger than the ln of x. That's why the limit, when we're taking the ratio, we get infinity. Now, it will be the same, even if I take the square root of x, also the limit is going to be equal to infinity. So as far as growth behave, the function that goes to infinity the fastest is ex, goes the fastest to infinity, followed by x to any power, as long as it's a positive power, and then followed by ln. So I usually tell my student ln crawl to infinity, goes very, very slow, and the ex basically run to infinity. It goes very, very fast. And these are the behavior of some basic function that we should, it's very important for us to really understand their behavior. So this is a very, very quick review of limit. And because we're gonna start using them tremendously as of this section. So now we're going to introduce the idea of improper integral. To introduce this idea, let me remind you a little bit, what is integral from A to B? Our definition. Okay. Definition of the integral from, you don't have to write, I'm just telling you, putting you into the idea of this section. And how did we basically define this integral? We took, that's the definition, the Riemann sum. We took the interval from A to B, that's a finite interval. We split it into pieces, that's what we did. And then we took f of x times delta x, we added those values. And then we started taking more and more subdivisions and found what happened when the number of subdivisions increases and increases. That was our definition of the definite integral. There is no other definition. So we started with this integral, and then we proceeded. Now we're going to extend the definition of the definite integral to what we call infinite domain. It means we're going to make sense out of the following idea. Integral from A to infinity of f of x dx. But the problem is I cannot use this definition anymore, because in the first one, I divided the interval AB. So if I put A to infinity, the question is, what am I talking about? The definition here that falls apart. I cannot take the interval from A to infinity and split it into pieces. It's from A to infinity. So the question is, what does this mean? And that's really the goal of improper integral. It's to extend the idea of definite integral, integral from A to B, to the idea of the integral from A to infinity. How we're going to extend this idea. To motivate this, we're going to use the idea of area. So to motivate our definition of that, I'm going to use the following idea. Okay, suppose I tell you, so that's a motivation for the definition. Okay, suppose I give you this kind of problem. Find, so problem. I tell you, okay, let us consider the following region. Let us consider the quote-unquote infinite region S, which is that lies under the graph of y equal 1 over x. So 1 over x squared. So it's the infinite region that lies under the graph of y equal 1 over x squared above the x-axis. And to the right of the line x equal to 1. Okay. All right, so I have the following region. So my region is the following. 1 over x squared, that's 1 over x squared. And the area that lies below this, below the graph, above the x-axis, and to the right of this interval. That's my S. It keeps going forever. And the question is, oh, what's the area of S? And really, what do we mean by the area? So it means if I compute the area of this region, what does this mean? Okay, so the question is area of S. It was a big question mark because that's an infinite region. So what do we mean by the area of S? All right, so how are we going to do this problem? So to do this problem is we're going to compute the following. So let us compute the following area. So this is an infinite area. I have no idea what I'm talking about, but let's compute the following areas. Right, I'm going to take the same region, and I'm going to compute the area. This is my 1, but I'm going to compute it up to 10. So this is y equal x, 1 over x squared. I'm going to compute this area up to here. This is a finite interval. Computing this area is actually not problematic at all. So let's compute this area. This area is the integral from 1 to 10 of 1 over x squared dx. Okay, which is going to be equal to 1 over x squared. We've done this antiderivative several times. It's minus 1 over x from 1 to 10, which is going to be equal to minus 1 over 10 minus 1, or 1 minus 1 over 10. So if I compute it up to 10, that's the area I get. All right. Now I'm going to take it, and I'm going to push myself a little bit. I'm going to compute it up to 100. So this is a 1. It's the same area, but I'm going to push a little bit. I'm going to push a little bit to the right and keep computing more areas. So I'm going to compute it up to 100. And this is the same thing, but over a larger interval. I will do that. What's the area again? So it's the same thing, but now I am changing the upper limit. That's really what I am changing. My upper limit is changing of 1 over x squared. Equal. Nothing is changed. It's the same function. I'm only changing the upper limit. Only changing the upper limit. I do that. What I'm going to end up with is 1 minus 1 over 100. Okay? All right. I'm going to keep going. And you're going to get bored, of course. So I said, all right, let me keep pushing myself. Let me compute the area up to 1,000. What's going to be the area? Again, the only thing I'm doing is I'm changing the upper limit of the integral. That's really what I am doing. It means minus 1 over x between 1 and 1000. And then what's going to happen is 1 minus 1 over 1000. Because I keep pushing and I keep pushing, and the area up to 10 is 1 minus 1 over 10, minus 1 over 100, minus 1 over 1000. So what do you guys say? What will be a logical answer for the area of S? What do you think will be a good? What do you think is going to happen to the area as we increase and increase the interval?
It's gonna get closer and closer to 1.
Go ahead, repeat.
I said it's gonna get closer to 1.
It's going to get closer and closer to 1. I mean, even if I compute the integral up to 1,000,000, I'm going to have 1 minus 1 over 1,000,000, or 1 minus 1 over 10 million. So the area is going to get closer and closer to 1. So the area is, S is getting closer and closer to 1. Closer. And so it's kind of fair to say that, the area of S is actually equal to 1. So the area of S, it's fair to say that it's equal to 1. And it's so fair to say that the area of S, and this is where the notation is going to be defined to be the integral from 1 to infinity of 1 over x squared dx, we're going to be equal to 1. Okay, so I will write, so now the formal definition. How we're going to write the definition. So definition. Integral, suppose A is a finite number. Integral from A to infinity of f of x dx. How we're going to define it. Okay. What did we do here? What did we do here? We computed the integral from 1 to 10, to 100, to 1000. So we repeated ourselves 3 times. We did the same thing 3 times. What did it change every time in this process? What did it change? No, not the 1. In this process here, what's the thing that
we changed the upper value?
We changed the upper value. Beside this, did we do the same thing? We changed the upper value. We computed this integral, whether it's the same way to compute this integral, but we started changing the upper value. So the idea is, instead of doing this process 3 times or 4 times or 5 times, why don't we do it once? And then by changing the upper limit, so instead of doing it 3 times, the idea, okay, why don't you do it when the upper limit vary, do it once, and then let your upper limit go to infinity. And that's really what the idea of the improper integral. So instead of doing it 3 times, that's what we'll be doing tomorrow, the idea, okay, fine, why don't you do it once? Up to t, and then you can let t goes to infinity. Doing it this way, you can do the whole process without having to do it 3 or 4 times. And that will be our definition for improper integral. So of course, I stop here today. You may not be able to do the homework on my lab, which isn't really a big deal, but I want you to finish totally the integration strategy that I gave you. And I will discuss the second page tomorrow, and we will cover completely the improper integral. Okay. All right. The class is dismissed. Those who have questions, as usual, can stay. The others can leave.
Have a good day.
Thank you.
Thank you.
So bye-bye, guys.
So the picture that we're looking at now, the answer to that would be A
Yeah, here.
on the theorem.
I will discuss it clearly tomorrow. That's why I stopped, because
Oh.
I need time. The way we're going to discuss is the following. You're going to compute the integral from A to T of the function. Instead of doing it 3 times or 4 times, we compute up to T. Then once we find a formula for it, we let the upper limit goes to infinity. That's going to be my definition for tomorrow, all right?
Okay, sounds good.
Make any sense?
Sure.
A little bit, yeah. I mean, that's exactly what I'm doing. I mean, the idea is that, you know, why you're doing it 3 times, do it once. Find a formula, and then let your upper bound go become very large and see what happens.
Right.
That's
thank you.
That's the idea. Sure. Anybody else? Is there anybody else anyway? Anybody has any other questions? Do you know of any reapplication for integral? I've always wondered. Integrals, area, volume, work, center of mass, that we didn't do in this class because somehow the book doesn't have it. So everything you guys will see in physics basically will be an integral. Israel? Israel, are you with me? Yes, you understand what I said? Volume, that's an integral. Area, that's an integral. Work, that you guys will do that a lot in physics. We did some, but in physics you will do a lot of work. That's absolutely an integral. There is the idea of the center of mass, which is somehow the book did not cover. Every other book does. It means if you take any object, and you want to ask yourself, okay, where does it balance? That's going to be an integral. Okay, so a lot in physics. I mean, most of the formula in physics, most of them are going to be an integral, believe it or not. All right, any other questions? Okay, see you tomorrow. Bye.